Icenene's a leading manufacturer of spray foam products. It's not going to be a commercial advertisement this afternoon that I'm giving you. However, I hope to really give you a bit of an overview of some of the latest changes to energy efficiency requirements in the building codes, and give you a sense of where things are going if they're not there already in your particular state. So with that as an introduction, I'd like to thank you all, welcome you, good morning or good afternoon, depending on where you may be. We're broadcasting over many time zones, so I realize that some of you might have made time available either before or after lunch, and thank you for that. Today's presentation is basically a presentation of Icenene as part of an overall effort to increase the services we provide to architects, engineers, and other design professionals. Basically, this is ultimately going to end up in being an AIA presentation. The content of this is fairly significantly oriented towards code provisions, how to meet them, and how to excel in your designs as you move forward in the years ahead. The content of this particular presentation has several sections. Basically, we're looking at a foundation starting from the key aspects of the code that we're going to be looking at, trace that through the various versions of the code, specifically focusing on things like thermal and moisture requirements, fire safety, integrated solutions, commercial fire testing, health and safety, and ultimately, we know that's where you want to end up, so we wanted to make sure we have a sound foundation for getting there. Basically, the requirements that I'm going to speak about are covered in both the IRC and the IBC, as well as sections of the IECC and ASHRAE 90.1. And you can see some of the key references there. In the IRC, we're looking at sections 806.5 and Chapter 11. In the IECC, there's snippets all through the IECC, as well as ASHRAE 90.1, particularly where we're talking about building envelope elements, walls, windows, roofs, that sort of thing. In terms of fire safety, we'll focus on IRC section 3.16, and we'll look at IBC section chapter 26, and that's basically the parts of the code that describe how materials are to be tested and specific tests they have to go through to be code compliant. So let's move on. Let's talk about the first of the things that I wanted to talk about here today, thermal and moisture control requirements. And basically, thermal and moisture control requirements that you would be adhering to would vary based on two things. One would be your geographic location, and the other would be the particular state that you're designing for, because that dictates what version of the code that you would be working to fulfill. And of course, code is what some people call the minimum you have to do to stay out of jail. Lots of folks are designing over and above code, and that's part and parcel of what we'd like to cover as well, give you a sense of how you can do that properly and not get yourself into trouble. So with that as the focus, the thermal and moisture control requirements that I want to talk about are basically going to start with the particular state that you're in. And you can see this is put together by a group called the Building Codes Assistance Project. Basically, these folks track which states are on which codes. So if you're not sure exactly what code your state is on and how to relate it to the talk that I'm giving here today, you can see the darkest of the states are on the IECC 2015 or the IRC 2015. The progressively lighter move back in time through 2012, 2009, 2006, etc. And I really wanted to use that kind of context to give you a sense of where we've come from, where we're going to, and why. Basically, what we're going to talk about is the evolution of codes and try to give you some of a directional feel on where we're going. 2006 was a significant code year in that it really solidified the current thing on vapor retarders. It had introduced 3 classes of vapor diffusion retarder, class 1, 2, and 3, with specific code provisions for each one of those categories. A class 1 or class 2 vapor diffusion retarder is basically the old vapor barrier that was required on the interior, and the way this code got solidified, class 1 or class 2 vapor diffusion retarder was required on the interior in climate zones 5 through 8. The 2006 code is also significant in that it is the first code that acts as a reference for the HERS scale. If you've been doing any design in residential, you know that there's a lot of emphasis in residential construction, particularly for energy rating of buildings. And the 2006 code is significant in that it sets or a HERS target of 100. And from there, if you make energy efficiency improvements, you're basically comparing in subsequent codes and in buildings designed over and above code to this HERS target of 100 under the 2006 code. So basically, if you were to say 20% over that HERS target, you basically have a HERS score of 80. 80 compares to 100, it's 20% less. And that's the way the HERS scale works. So that's an interesting little aside. The IEC 2006 is also significant in that it was a very flexible code. Lots of trade-offs were allowed. You could trade off energy efficiency improvements in mechanical systems against windows or building envelope components. Lots of flexibility there. And so it's one that sort of a number of folks look back on longingly. If only we could have the flexibility of that code when we're striving for more. And we'll talk a little bit more about that as we go further into this discussion. So looking at the IRC and the IBC, for that matter, in terms of how those codes relate to climate zones, you can see that climate zones more or less form bands across the country. Basically, the most southerly band is climate zone 1, and that's sort of everything south of Alligator Alley in Florida. Basically, the southern tip of Florida is climate zone 1, and then you can see the Gulf states are climate zone 2. Through the middle part of the country, we have climate zones 3, 4, 5, and 6, and then there's a little bit of climate zone 7. And climate zones 7 and 8, interestingly, extend up into Alaska and lots of Canada as well. So that's the way that code divided up the country. And what was significant, once again, is that the dividing line of 4 and 5 is where we transition from an area where you do not require a vapor diffusion retarder barrier on the inside of building envelope assemblies. When you move above climate zone 5, you get into the requirement for a vapor diffusion retarder on the interiors. So let's move on. When we move on to 2009, that code introduced air tightness levels on the residential side of things. It also introduced aggressive insulation values, both on the IRC and the IBC. And you can see the way things stepped up there. Basically, for much of the country, it was a requirement that we moved from 2x4 to perhaps 2x4 construction with insulating sheathing, or 2x6 construction. Basically, 6 inches of construction accommodates R20 in the walls with more dense hit R21, and that was required in zone 7 and 8. Not every insulation material meets that requirement. So one of the knocks against the 2009 code is it was kind of proprietary in nature. Some products were winners, some were losers, and it basically played favorites in terms of materials and where they could be used. The other thing that's significant about this code is it sets a HERS target overall of about 85. So that's a 15% saving over the 2006 code, which was a HERS target of 100. Moving into 2012, the air tightness levels required of buildings were starting to get tightened up. Everything above code zone 3 basically has to be tested at an air tightness of 3 air changes per hour on the blower door test. That's residential buildings, but there are requirements, barriers, and continuous insulation starting to creep into the IBC as well. You'll see that proprietary insulation knock against the 2009 code gets taken off the table because basically a bunch of the climate zones now in this code require a continuous layer of insulating sheathing on the exterior. And you kind of see the impact that has. Basically, the HERS target for this particular code is approximately a HERS target of 70. So basically, that's a 30% saving over where we were just 6 years previous. So we're starting to see codes ratchet up very quickly, and it's having a substantial impact on the way buildings are built. When we move to the 2015 code, much of the insulation and air tightness requirements remain virtually unchanged. There's a little bit of tweaking, but you probably won't notice it in any of the drill down into some of the codes documents to get the subtleties of some of the changes that were made. But one of the significant things that was done was this code actually introduced what was called an energy rating index. So it didn't focus on the HERS scale, but it basically envisaged that there would be scales used to, as a performance path for meeting this code, make it a little bit easier, a little bit more flexible, and you do that by way of the energy rating index. The HERS scale qualifies as an energy rating index, but it may not be the only scale that's out there. There are others who are trying to develop their own in competition with ResNet and other providers. The commercial code evolution is pretty similar, and you can see that depending on where you are in your states, you're probably on a similar version of the IBC or the ASHRAE 90.1 standard that is called up by the path. So basically, as we get into 2010, 2013, we're seeing requirements for continuous insulation. We're seeing requirements for continuous air barriers. Commercial buildings, of course, are larger animals, and they're finished in stages, so it's more difficult to do things like air tightness tests. So it's more a requirement of component assemblies, code-compliant construction, that sort of thing. So basically what we see if you drill down into the text of the IBC and the IECC for commercial buildings is a consistent message with the IRC, higher insulation levels, generally requiring continuous insulation. That means insulation that's not interrupted by studs and wall framing, typically outboard of the wall assembly behind the cladding. But that's not necessarily the only place it can be placed. And incorporate a requirement for an air barrier, which either requires certain types of air barrier materials to be used, or various systems that join and link those materials to be included and tested. And that's what a lot of manufacturers, like ourselves, have spent a lot of time and energy doing as the codes have been ratcheted up. Basically, when you go to the IECC requirements for commercial buildings, you see some subtle differences where they actually use a more of a sharp pencil approach to the continuous insulation requirements instead of R13 plus 5, R5 continuous insulation to R13 plus 3.8. Somebody's done an exact calculation that basically links continuous cavity plus continuous insulation to cavity only equivalents. And so you can see how that reads out through the entire table, as well as below grade and other applications. What else you can find, if you really drill down, you can find some specific testing that's called out for air barrier materials. Basically, the key sentences are listed there. IECC sentence C402, decimal 5, decimal 1, decimal 2, decimal 1. Bit of a mouthful. But that basically lists performance as measured on a full wall assembly test called ASTM E2178. So it's not just that the material itself performs as an air barrier. You start to get into these assemblies that are tested. The assemblies get more complicated as we look at tests like ASTM E2357. That test basically incorporates things like plumbing penetrations and ductwork and windows penetrating wall assemblies. And basically the requirement is to comply with the standard. The joints must be sealed with materials meeting their barrier material description a little bit higher in the page. So these things tend to combine and build upon each other and work with each other. The notion is that buildings are now more than ever being viewed as systems that have to be done in their entirety properly to get the next stage of benefits of energy efficiency as well as comfort and durability performance. Moving on, if you look further into the IECC, it calls for something called a water-resistive barrier. And you might have heard this in presentations from leading building scientists over the last few years, talking about things like a drainage plane or a weather barrier. The concept's pretty simple. Basically, the barrier that's being required is something that's there to limit the ingress of wind-driven rain. And if you think about your roof, for example, it's shingle lapped, basically lapped so that things run off the outside and are directed back to the outside. Basically, that's the way to think about barrier in walls. It's the same kind of philosophy, that lapping and layering to make sure water that happens to penetrate into the wall has a means of draining downward and outward back out of the wall, so it won't cause any long-term damage. The vapor control requirements that are in the code are actually kind of interesting ones. There's a requirement for Class 1 and Class 2 vapor retarders on the interior of zones 5, 6, 7, and 8, as well as Marine 4. So that, by definition, implies that vapor retarders are not needed on the interior of zones 1, 2, 3, and 4. Basically, what happens in those zones is the humidity on an annualized basis, and even for the vast majority of the year, is higher on the outside of the building than it is on the inside. So you wouldn't want a vapor diffusion retarder on the interior to cause moisture diffusing in from outside to build up at some point portion of the wall. That's why it gets eliminated. So it's important to realize that not only does the code not require you to do it, the code basically is inferring that you should not do it in those situations. The code also has some other language that not too many people are aware of. There's a table in section 601.1 where it lists where Class 3 vapor retarders can be used. And Class 3 vapor retarders are actually interesting. Light density foam qualifies as a Class 3 vapor retarder. We think of that as being open cell foam, but it has an ability to, in a limited way, control vapor diffusion such that it won't be a problem in certain types of construction. basic paint, 2 layers of latex paint will qualify as a Class 3 vapor retarder as well. So whether or not you intended it to be, the minute you paint drywall, you actually are applying a Class retarder on the interior surface of that material. So it's important to realize the implications of that. Basically, when you do that, this is a very interesting table that you will find. If you go down to the bottom of each of these categories, you'll see that when you apply insulated sheathing, even in zones 5, 6, 7, and 8, basically continuous insulation, you basically end up at a point where you don't need a Class 1 or 2 vapor retarder on the interior. And why is that? Well, basically, the insulated sheathing, or continuous insulation, if you will, has the net impact of warming up cavity spaces on the interior of the wall such that there isn't a risk of condensation. And so it's interesting to see that these requirements with continuous insulation kind of dovetail with better durability and moisture control, keeping interior vulnerable parts of and drier. And so then you can go to something that's more vapor open on the interior to take advantage of that and allow drying of incidental moisture, something that might get in there from construction or a very small leak. Allow that to dry to the interior. So that's an interesting bit of flexibility, and it kind of shows you how codes folks are looking at continuous insulation, higher insulation levels, vapor and moisture control as part of an integrated solution. And that's kind of where folks who get a real handle on this are going with building design. So that sets the stage for us to talk a little bit about the next element I wanted to drill down into, which was fire safety. And so continue on with me. Fire safety is section 3, and we have a few more sections to go. So with no objections, I'll keep moving as quickly as I can. A lot of in continuous insulation, air barrier applications on the exterior of walls are in fact combustible materials. And so a lot of designers frequently ask me the question, well, how can you use that in non-combustible construction? Well, the fact that non-combustible commercial construction is intended to be non-combustible doesn't mean that it doesn't have some combustible elements. And the best example I have is how much wiring is there in walls with plastic sheathing, something that would in fact be combustible. We take it for granted. So there are allowances within the code to use combustible materials in non-combustible construction. But the requirements of the code are structured in certain ways to require a couple of things. The code requires a certain amount of non-combustibility in the materials that you use. So basically, it requires you to do tests, parts being a part of the materials that are added. And you think of things like cellulose having borate and in some cases other fire retardants in it. Plastic materials have their own specific types of fire retardants depending on which type of plastics that you're looking at, and so on. The key thing that the code requires for these materials is that testing be done on the assemblies in which they're used to make sure that the assembly overall isn't compromised. It still maintains its non-combustibility rating. And we'll talk a little bit about that in greater detail. The one thing I'd like to point out at this point in the discussion is, obviously I'm here to talk a little bit about spray polyurethane foam. People, for some reason, have the impression that spray polyurethane foam will melt when it actually gets heated. It is of a class of materials that we call a thermoset plastic. Basically, the A side and the B side combine spray polyurethane foam, and the resulting material is something different than either the A or the B. It doesn't go back. And so when flame or heat is applied to spray polyurethane foam, it doesn't melt, rather it chars, which makes it a little bit different from other thermoplastics, things like expanded or extruded polystyrene, which do have the capability of melting and running out of the wall. So it's important that we as manufacturers test our specific material and be able to furnish to you specific data that confirms that our materials can perform in the assemblies that you're looking at, and we'll talk a little bit about what those tests are. Basically, the code assumes, as I said, that any kind of plastic material, foam plastic, is a combustible material, and so as such must be covered on the interior by a thermal barrier. But the code doesn't leave it at that. It gives you some very specific solutions for a thermal barrier, and you can see at the lower left-hand side of the slide that the code prescribed thermal barrier is basically half-inch gypsum applied over any foam plastic on the interior. Now, in some applications, not directly connected to the occupied zone where access is limited, the thermal barrier can be omitted. And why is that? Well, basically, if you look at a space like an attic space, it's not directly connected. There will be a half-inch drywall that separates the attic from the occupied zone, but up in the attic itself, there's a space up there that could be occupied from time to time for repairs of mechanical systems, electrical work, that sort of thing. And the vision there is, in those applications, you would need an ignition barrier over foam plastic or combustible materials. And some of the prescribed options here are things like 3/8" gypsum board, inch and 1/4" plywood is viewed as being suitable in those applications. A lot of manufacturers like ourselves have materials tested which can actually go without the code prescribed ignition barriers because they've passed specific tests that indicate that they're not combustible enough to warrant the need for an ignition barrier. So anything that's listed as a prescribed option within the code can be superseded by actual testing that manufacturers have done on their specific products. Some paint manufacturers have intumescent paints, which will be resistant to fire enough to form an actual thermal barrier over spray foam products and other foam products, for example, and they should be able to provide you with testing that points that fact out and backs it up with third-party research. If you look at tests that actually qualify those non-prescriptive alternatives to ignition and thermal barriers, there's lots of examples and lots of options that are basically out there testing for thermal barriers under at least 4 different standards, as well as other ones that the end-use manufacturer might come up with. Typically, the way these materials get specified is the testing that they will provide you will show you the maximum thickness of insulation that can be used and the minimum of thickness of coating that is required over that insulation. So basically, when a manufacturer does a test, say with 12 inches of insulation and 20 wet mils of coating over top of the assembly, typically the approval is for anything up to 12 inches of insulation and anything above 20 wet mils of coating. So that's the way these tests work. Okay. In terms of the types of materials that manufacturers can provide to you to basically document the testing that's been done, we don't expect that everyone on the phone here will be experts in reviewing test reports and know whether they're legitimate or not. We leave that to groups like the ICC Evaluation Service, and they produce what they call Evaluation Service Reports, or ES reports, and they will list the prescribed solutions available in code, as well as coatings that have been tested over the product in specific ignition barrier and thermal barrier types of assemblies. And so you'll see a bunch of prescribed solutions. Basically, coming down the page, the types of tests they will list will be specific tests for areas like attics, floors of attics, crawl spaces, and generally as required for thermal barriers tests directly in the living space, and the approval that will be given for that specific material, the foam and the coating, will be for, as I say, the maximum thickness of foam and the minimum thickness of coating. So if a manufacturer's only tested 6 inches of foam, then unfortunately that's the way the code official is going to look at that evaluation service report and just basically say, oh, you can use anything up to 6 inches, but if you're going to use more than 6 inches of foam, you probably need the manufacturer to supply me with another test. And so when we get into non-combustible assemblies, commercial assemblies, the requirements kind of spread out a little bit here. Basically, in non-combustible assemblies, there's a basic test that we call NFPA 285. It's a full 2-story wall assembly with intersecting floors and windows, fairly that has to be made. And basically, that will be the first step in proving that a particular material, be it an insulation material or a weather-resistant barrier or some other synthetic material, it's the first step in proving that that can be used in a non-combustible assembly. The next test that they'll want to see is what's called a potential heat of the combustibles. Basically, NFPA 259 is a small-scale test and talks about how much heat is released. So it allows them to take the amount of heat released by the material and basically do some comparisons to other wall assemblies, other types. You can appreciate that there are dozens, if not hundreds, of perhaps even thousands of different alternatives for wall assembly configurations, and it would be impractical or practically impossible to test all of those assemblies. So what's done is they will take steps to understand the specific thermal. That test that has been done can be translated to other types of assemblies by means of an engineering analysis, or EEV. The final test that's typically done is ASTM E119, which is a test that many of you might be familiar with. Basically, that gives the hourly rating of the assembly. So now we know that we have a non-combustible assembly, and with the specific materials that are in place, we could believe that that assembly is either unrated or has a 1-hour fire rating, a 2-hour fire rating, or perhaps even a 3-hour fire rating. And this may surprise you, is that there are lots of insulated assemblies with spray foam and other synthetic materials that actually have a 3-hour fire rating as part of the approval in their ICCES reports. So that's significantly different than you may have been given to understand prior to this talk. So that gives the basic starting point I wanted to talk about, and that is integrated solutions, and give you a sense of where I'm going with this talk. Basically, to do that, I've got to go into basics of what is spray foam. A lot of folks think of spray foam as being an insulation only. If you take it back to its fundamental roots, spray foam is different from many other insulation products in that the liquid components that are put together, or poured and sprayed in place, basically expand into a foam plastic material that accomplishes 2 functions. It both insulates and air seals. So the foam is fulfilling both these functions in the assemblies to which it's applied. And depending on the foam type, it may have other characteristics as well to allow you to add other performance into your wall assemblies. When you drill down into the The technical jargon, foams described various and sundry ways. Some folks will speak of low density and medium density foam. Other folks will speak of half-pound or 2 pound. Basically, that corresponds to half-pound per cubic foot density or 2 pound per cubic foot density. Some will speak of open cell or closed cell. You may just know it as some foams are soft and flexible, other foams are hard and rigid. And basically, you can see the way the two families of foam break out. The medium density foams are the 2 pound closed cell hard rigid foams, and the low density spray foams are typically in the range of half pound or maybe slightly more per cubic foot. Commonly called open cell material, soft, flexible foam if you pick it up and touch it and try to squeeze it. Both of these products are evaluated by the ICC Evaluation Service and other evaluation services, and both 1 to 4 construction if the manufacturer has done the appropriate testing and formulating of its materials. And there's a requirement in both the low density and medium density standards. For obvious reasons, these products must be installed by trained, qualified installers. It's not something that you can go to Home Depot or Lowe's and kind of pick up and do it yourself. This is a professional grade insulation air sealing material. Some other characteristics that you may not be aware of is when we talk about open and closed cell foam, the open cell refers to the microscopic characteristics of the foam itself. If you can picture foam being made up of tiny bubbles, if the bubbles are open from one bubble to the next, that's an open cell. It basically is called open cell based on the degree of openness between the microscopic bubbles. And the way standards are written, anything less than 90% closed cell is referred to as an open cell material. So that's quite significant. Even open cell material has closed cell content. And the closed cell content is what folks think of for giving performance like things like air barrier and air leakage control, which is why both the low density and the medium density spray foams can act as air barriers as well as insulation. The reason closed cell content is important, particularly in medium density foams, is that there is a captive blowing agent that is part of medium density foams. And you can appreciate if the little bubbles aren't closed, then the captive blowing agent can get out and some of the insulating value will be lost. So it's very important that medium density foams retain that blowing agent because it's part and parcel of the added R value that comes with that product. Open cell products typically environment over the first few days and weeks after spray, and typically the cells get filled up with air. And so as a consequence, you'll see the medium density foams have a higher R value per inch than the low density spray foams. But if you go back to that notion of density, it takes probably about 4 times the amount of material and all of the embodied energy and other resource inputs to make medium density foam. So you typically find that if you've got the space and you've got the ability, low density foam is probably the least expensive way to get a lot of R value into a space, as well as getting that air barrier performance. So you can kind of see where the two types of foams might be used. If you've got constrained space applications, medium density foam is your choice. If you've got a more open cavity to insulate, well, you probably should be looking at low density in that particular space slash. The rest of the story, just taking it a little bit further, some of the things you might not be aware of. The medium density foam, basically because it has that high R value, when the reaction takes place to form spray foam, basically it releases heat. And if you've got a fairly high insulating value, in the material that's produced, that heat can't escape. So typically, medium density foams must be sprayed or laid out in layers so that the heat has a chance to dissipate before subsequent insulation is added. So the way medium density typically gets applied is it's applied in 2 to 3 inch layers. It will be a rigid material, as I spoke of. That makes it kind of difficult to trim. So typically a trained installer will be looking to try and underfill just a little bit the cavities that are available with medium density foam. Whereas low density might be sprayed and installed, and it dries a lot easier to trim, a lot easier to work with, and the excess material typically gets sawn off or what we call scarfed off, such that the cavity that's left is fully filled with spray foam, and it's the low density insulation and air barrier material. So I frequently at this point in the talk get asked which foam is best, and I have a fairly simple response. It depends on your design objectives, the application, the available space, the needed R value, and other properties. And of course, cost is always an issue. You don't want to spend more than you need to get the performance that you want and need. So there's a bunch of trade-offs that you've got to be cognizant of and be able to handle to do the job properly. So that kind of leads into my next section. Basically, I wanted to talk a little bit about commercial fire testing. I mentioned that the commercial fire tests that are typically used as the basis for entry into the game are predicated on a couple of fire tests. One of them is NFPA 285, the multi-story building test for combustibility. And typically, in these assemblies, you try to show the combination of materials that will be applied will, in fact, meet the requirements of non-combustibility. I wanted to give you a bit of a sense as to where these types of tests go when you use real-life examples with real-life materials. We used a typical 5/8 gypsum board on the interior, like the type of fire-rated gypsum board that you get in hourly rated assemblies. And we sprayed a full cavity, 6-inch cavity, full of spray, open cell spray foam in the interior cavity. And we put another 6 inches of continuous closed cell spray foam on the exterior and covered the spray foam. There was a level of dense glass gold in between those materials, and there was a cladding on the exterior. Now, the cladding on the exterior of this non-combustible, quote-unquote, wall was nothing more than 1/4-inch hardy board. So it was a pretty minimal coating to ensure, basically, that we didn't have direct flame impingement on the spray foam. Basically, when we put that assembly together and tested it, we passed with a 1-hour fire rating. When we put that assembly together, we passed the non-combustibility test. We added a 4-inch brick on the exterior, and we passed a 1-hour fire rating with that. And what we did was we added nothing more than testing for an extra hour. And basically, when we did that, we were able to take that same assembly through a 2-hour fire test. And so what we found was this basically opens the door for a number of applications for foam, basically with a non-combustible cladding on the exterior, either brick or a non-combustible cladding meeting ASTM E136. You can use up to 6 inches of foam continuously on in the cavity space towards the exterior of the building. You could use a combination of 6-inch foam on the exterior plus 6 inches of foam on the interior, a full 12 inches of foam in that assembly. So you can run value when you have that much spray foam in an assembly. Or you could combine spray foam with other board sheathing products and non-combustible claddings and get any kind of combination that you wanted. So that represented a fairly significant breakthrough that folks were soon to realize, hey, this provides some options in terms of the way I'm designing my buildings. These assemblies are code compliant in terms of fire, and you can make tweaks to them. If you'll recall the way I described fire testing before, we've got fire testing at the extreme. So if you want to use less than 6 inches on the exterior, that would be covered based on the fire testing that's been done, because we've tested up to 6 inches on the exterior of those wall assemblies. So interesting stuff. So then we get into design and why we're starting to see in multiple applications like this. Basically, I mentioned the function of insulation and air barrier. Basically, by including spray foam in an assembly, you can, it's not the total solution, because other transition membranes will be required at control joints and changes in construction, but it's a huge step towards this continuous air barrier system, and it forms an integral part of things like a durability plan, because the notion of vapor permeability, low air leakage manages to control a lot of moisture that can get into building envelope assemblies. If you're using a medium density foam in a particular application, it can also have the duplicate function of a vapor diffusion retarder. Typically, these materials at 1.5 inches or 2 inches thick will have the ability to be code compliant in terms of vapor diffusion retarder, which we said previously is what's required in zones 5 and above. And that characteristic of low water absorption as well as low vapor diffusion forms a key element for other features like a water-resistant barrier system. There you would transition to through-wall flashings and other similar materials to complete the package, so that the insulation on the exterior of the wall assembly is both continuous insulation, air barrier, as well as water-resistant barrier system. And you can see the way some of these things come together. So now we're getting into the meat of this. I wanted to take one last detour. I want to talk a little bit about health and safety, because whenever people are talking about spray foam, I'd like to use the opportunity message to a learned audience. So thus far, I guess I've kind of inferred it, but I'll say it very directly. What I've been talking about is a product, or a family of products that we call high-pressure spray foam. And many of you would know this based on the fact that they come in truck-based spray rigs. The product is typically sold in what we call sets, 2 55-gallon drums, an A side and a B side, and those drums contain approximately 500 pounds of material each. That material is drawn out of the drums through a proportioning unit that's in the truck, forced down a set of parallel hoses, and they get mixed together at the spray nozzle or gun that the applicator uses. So they stay separate right down to the end of the line until they come together, and once they come together, reaction instantaneously begins to take hold. Basically, they're pumped down the spray line at a pretty high pressure. 100 psi is the typical pressure that we'll see in those hoses. You can kind of relate this to your home water faucet. Basically, household pressure in your home for your water system would be in the range of maybe 40 to 70 psi. So it's approximately 1/20th of the pressure of what we see in these guns. So they're not toys. That's part of the reason we want to make sure that they're administered by trained installers, and that's the emphasis that we as a company and I think our whole industry is making in terms of product stewardship. The other thing that I point out is that these are reactive components. So the A side reacts with the B side to create a new product, something completely different from the two starting products. And that reaction takes place once the two raw materials are brought together in the spray gun. The materials surface, so that results in some aerosolized particles and the possibility of a little bit of VOC emanation from the material as it's being sprayed. So because we want to be as safe as possible, we make sure that our workers are covered in tight-fitting coveralls and are provided with a separate air supply directly from outside, so they're not breathing in the spray as it's applied. You wouldn't want to breathe in spray paint. You don't necessarily want to breathe in spray foam while it's being applied. So when you're including spray foam on a job, we usually have a requirement that we set forth as manufacturers to exclude all non-participants, if you will, from the work area during the spray process and for a period of time afterwards. Typically, I've talked about foam as being two generic families. The medium density foam has typically things like polyols. They're the kind of the backbone that react with the isocyanate and the A side. Catalysts that control the reaction, surfactants that cause the whole solution to blend together, some flame retardants, water, and a blowing agent. In the light density foam, typically the blowing agent is the water itself. Water will cause isocyanate to react. So basically, the principal difference between light density and medium density materials is the inclusion or deletion of the synthetic blowing agent, and typically the light density materials have a higher content of water to get the reaction to form. But all materials are not created equal. Each manufacturer has their own proprietary solutions for both medium density and light density foam, and that particular formulation, if you will, results in unique physical properties. And so the physical properties of an isonine product would be different from other manufacturers that are out there. So because the formulations are different, so too the approvals vary between manufacturers. So it's really, really important, as I say, to keep an eye on the specific approvals and testing that manufacturers have done. And while we're on the subject of health and safety, I just wanted to give you a little bit of a sense of how spray foam typically gets applied. It gets applied in a confined, not a confined workspace, a workspace that is enclosed basically to make sure that all of the spray foam activities are kept separate from adjoining or adjacent activities. In new house construction, it's easy enough to do. Basically, the insulating trade goes in on their own day, and other trades follow at some point thereafter. What we'd like to do is have a mechanical fan in the work area to cause air exchange, and we'll specify that air exchange depending on how quickly you as a designer or a building owner wants to reoccupy the space. If you've got trades coming in very quickly, we might have a high rate of air exchange to make that a possibility. And we might specifically select low VOC products to allow you to do that. So we make sure that our workers are outfitted in proper PPE. We confined or enclosed the workspace. We're ventilating during and after spray, and we're keeping occupants and bystanders out of the work area so that we can basically do our work in accordance with best practices. And if you're dealing with Icynene products specifically, we've made a habit of having warnings specifically on our products and on our literature as well that basically list that we want to see for the specific products that you're interested in. Now, not too long ago, spray foam products generally were such that you had to stay out of the premises for 24 hours after the work was complete. Well, we've got formulations now that have low emitting catalysts and other product characteristics that allow us to have very swift reentries for trades. Especially, we could re-enter after 1 hour, but we could ventilate at 40 air changes per hour and have the whole area so it could be reoccupied after 2 hours, and that's good news. So those of you folks who were concerned that spray foam creates an environment where you basically had to hand over the workspace for several days, there have been breakthroughs in formulation and innovations in spray foam application that are allowing us to get ever quicker on the reoccupancy scale. And even if you don't want to reoccupy that, those spaces that quickly, it's VOC characteristics that work into some of the design objectives that you folks would have for your buildings. So that leads me to the final section of today's talk. And I know you've been waiting for this to kind of see how it all comes together. And with that kind of a background, hopefully you understand some of the elements that are going into these applications I'm going to talk about. So typically in walls above grade, we would see foam being installed, say, in residential construction, wood frame. The typical foam that gets installed on the interior is light density foam. It's basically going to be a class 3 vapor retarder if that's required, with continuous insulation on the outside. That's all you need on the interior. But to be code compliant, of course, you're going to have to cover foam with a thermal barrier. And that thermal barrier, as we said previously, is typically half-inch gypsum drywall. 1 to 4 construction, multi-story buildings and so on, you might be into rated assemblies, metal studs, multiple layers of gypsum, and there are approved assemblies in those kinds of applications. Basically, the key difference being if you want to get up to the higher level fire protection, you'll have multiple layers of gypsum on the interior. The testing that we've done with many assemblies has suggested to us that 2 layers of Type X gypsum will get you up to 3 hours of fire rating on a non-combustible assembly. So that's a major innovation. In terms of the exterior look of buildings, trying to get continuous insulation is part of the story. So medium density spray foam is the product of choice in this kind of application. The medium density is the closed cell. It is a vapor diffusion retarder. It can be a water resistant barrier. A set of transition materials around things like window openings, through wall flashings at intermediate floors, as you can see here. One of the details I like to see is having retention bars, something mechanically holding the top edge of that through wall flashing to the backup wall. And typically what that does, if you'll recall, medium density foam, all spray foams for that matter, are such that they create an exothermic reaction when they're mixed. And so that process of giving off heat may tend to in some cases, cause the adhesive, the bituminous material in those through wall flashings to melt. And so having that retention bar there makes sure that the material doesn't peel off in any way during the spray process. It also provides a mechanical interlock between the spray foam and the transition membrane to give you further assurance that you've got a continuous air barrier. So it's a detail I like. Other materials being used, a combination of sealants. The nice thing about spray foam is it sprays around masonry anchors to give you that nice tight seal with no additional work. So that's a major improvement. It simplifies construction. And what we're seeing in many cases is this, depending on the types of features you build into your walls, you can realize anywhere from a 10 to 20% saving in terms of labor, notwithstanding the fact you've gone to these extra steps to make sure that the leading edges of flashings are properly detailed. The nice thing about spray foam is it conforms to complex construction. So curves, no problem. Projections, changes in plane, that's one of the things that spray foam excels at, sealing up those gaps that other materials struggle to work with. You can do it with other materials, it just takes a lot more work. If you've got other materials in behind spray foam, it can be a nice belt and suspenders, basically. A little bit of redundancy in your design. So you may have specific designs that call for redundancy. You may have other ones where you're looking for an economical solution, and I think spray foam fits into both categories exceedingly well. The other key area where you'll find that spray foam solutions will make a lot of sense is areas where floors project over unheated or unoccupied space. Typically, this is where a lot of contractors, general contractors, got experience with spray foam. It was the only material that could solve those air sealing problems created by the big gaps that were created when you projected floors over unheated space. You need to put a thermal barrier on the exterior surface of the spray foam, typically an exterior gypsum, a water-resistant gypsum. Any of these sorts of materials can form that. The spray foam itself can be used to encapsulate surfaces and structural elements to eliminate thermal bridges and thermal shorts that would otherwise compromise the insulating of that space. So typically what we're seeing in large measure is a number of trends that are occurring, particularly in above-grade commercial assemblies. Obviously, if you're going to incorporate materials like spray foam and continuous insulation into assemblies, you're going to have a requirement for a thermal barrier on the interior. That's typically not that difficult to accomplish with a simple layer of drywall, be it 1/2 inch or 5/8 if you're looking for rated assemblies. The wall cavities, I've said previously, we've tested up to 6 inches of foam in wall cavities. On the exterior, we've tested approximately 5.5 inches on the exterior. Transition membrane from all of the leading suppliers have been tested for compatibility, so there's good messages there. I emphasize details with mechanical interlocks as well as adhesion bonds to those transition membranes, just to make sure that you're getting a proper job. And then, of course, a non-combustible cladding. The trends also, are dictated by code, calling for increasing insulation levels, use of continuous insulation in all climate zones, particularly as laid out in ASHRAE 90.1 and the IECC. We've seen a lot of designers trying wherever possible to avoid sheet vapor retarders by choice, to make sure that the materials that they have an inherent protection against moisture, an ability to breathe if that's called for in a certain aspect of the design. To that end, we're seeing the use of light density spray foam as both an open cell vapor breathable membrane on the interior. We're seeing medium density foam as continuous insulation, air barrier, vapor diffusion retarder, and water resistant barrier on the exterior. So that puts us at a point where we could entertain some questions. I thank you for this, for your attention to this talk. As we indicated, we're working towards having this recognized by the AIA, and so any feedback you can give us would be helpful. And we're, of course, going to be available for as long as it takes to answer the questions that may have come in. So I'll start with the ones that we've already received. It's been asked, is there the ability to get this presentation material after the fact? Adina, with the availability, our intention was to have it available on our website. So I think they're on the website, and we'll follow up with each of you with an email to give you the exact URL to tie into where the presentation is. I've got a question of what can be done when spray foam needed exceeds 4-inch thickness and it appears that the thickness exceeds the code limit. Well, if we're talking about some of the materials that I am aware of that we have, those materials on the exterior can be applied up to 5.5 inches thick, so you can go well beyond 4 inches. On the interior, you can add supplemental insulation in the cavity space as well. I'm thinking that the combination of 6 inches on the interior and 5.5 inches on the exterior is a combination that's going to more than exceed the requirements of most people at the present time. But if you have a specific wall assembly, foam then is laid out in ESR reports, I advise you to get in contact with the manufacturer, because they can take the testing that's been done and basically do a engineering analysis. A qualified fire engineer can basically take the approved testing and other characteristics of the material and determine whether or not that material would be suitable for the application that you have in mind. So get in contact with the manufacturer, ask the question. In cases like that, we would advise you to call the engineering department of Icynene for our particular set of materials. I'm sure all of the other major manufacturers out there have similar resources available. What is the cure limit for this application? Well, curing is one of these words that is a little bit different when you're talking about spray foam. Spray foam actually reacts fairly quickly with complete. So if by curing you're saying how long should you stay away from spray foam while VOC trace contaminants might be coming off the foam, there are foam materials that can be suitable for reoccupancy. That's a very difficult bar to cross, but they can be suitable for reoccupancy in as little as 2 hours. In most cases, most materials from most manufacturers are going to be in the range of 24 hours. So you may just sort of adopt a 24-hour requirement, but if need be, it's nice to have that 2 hours in your back pocket, depending on the materials that you're using. Next question, does 3.5 inches of closed cell foam between wood studs qualify as a Class 2 vapor retarder? And the short answer to that is yes, it does. However, some codes officials will give you pushback on the fact that the wall studs would compromise the vapor retarder, and you may to that closed cell foam. So typically, what we'd end up doing in that case is using using light density foam and filling the cavity with light density foam and just using the interior drywall with a vapor retarder paint. There are vapor barrier paints that are available that would meet the code requirement. Is there a requirement for distance of thermal barrier away from the spray of the surface, face of the spray foam? Good question. I didn't clearly lay that out. There are materials that can be painted directly on spray foam that qualify as a thermal barrier. These sort of are in the class of things like intumescent paints, and they're directly applied in intimate contact with the spray foam. Of course, drywall on the interior, there might be a bit of separation. Thermal barrier a little bit better because there's an airspace that provides insulation between the thermal barrier and the foam itself. But for any of the approved alternatives to the code-prescribed thermal barriers, basically those materials have been tested in intimate contact with the substrate, the spray foam that they were sprayed over. So there is no need for a gap. I would like to see a section through a flashing detail you were discussing. Thomas, give us a call at Icynene, and we'd be happy to work with you to get you what you need. Basically, the flashing details that I was showing, I elected to do it with photographs simply because most people relate to a picture better than they do to a detail. What I was trying to show you, in case you didn't note it at the time, was the leading edge flashing at the substrate level had a metal retention bar basically holding it in place. So there's not only the adhesive bond of the peel and stick membrane sticking to the backup wall, but there's also the mechanical bond of that retention bar tied into the backup wall and tied into the foam. So it creates two levels of insurance that you've got intimate contact and a continuous air seal. Is there a special type of closed cell that should be used in a wall cavity over CMU with a brick veneer face for moisture resistance, or will any closed cell polyethylene foam work? Interesting, good question. Most closed cell foams could work on warehouse construction. People might not be all that particular on anything that's going to be rated or whatever. I would say that you would be obligated to do your due diligence and get a system or material that the manufacturer has gone through the NFPA 285 as well as the ASTM E119 testing to qualify that material for building construction. That's sort of the starting point I indicated for commercial wall assemblies, but it's a good rule of thumb that closed cell foam tends to get used for a variety of applications. It could be used on storage tanks. It could be used in industrial applications. So there's some garden variety closed cell foams out there that wouldn't have the fire testing and other characteristics to make it suitable for building construction. So I would place the onus on you to make sure that you have something with an ICCES report that basically stipulates that the material can be used in types 1 to 5 construction. And that should open the door. And with that, I think we've handled all of the questions. If you have questions after the fact, by all means, get in contact with us at icynene.com. In addition, if you would like to have this presentation presented to you in your place of business, we have a number of architect reps throughout the country who are able to give this presentation or an excerpted version of this presentation to you as needs permit. There are a variety of AIA sanctioned presentations that you could take advantage of to get continuing education credits, as well as upgrade your technical knowledge on these important and evolving topics. So with that, what I'd like to do is thank you very much, and hopefully the information has been useful to you. By all means, if you have any feedback, construction you'd like to send off to us, we'd appreciate that as well. So thank you for attending.